So we're going to wrap up our lecture today by looking at the structure of the error in our modeling process. We're going to look at what are the components of our prediction error. So let's remember where we were. So we have observations y, which are the blue dots in our plot so far, and those observations come from a ground truth process, g of x, which is a mathematical constant, to which we add noise epsilon, and this noise has zero mean. And from these observations, we build predictions. We build a model y hat that makes predictions for any individual x. We have a prediction y hat of x. X will be fixed for now. And so the error in our predictions is y minus y hat of x, right? So we get a new observation. We get a new individual pair of x and its data point y, and we can make a predicted value, and the error is this difference. What is this made of? So first of all, let's think of where is there randomness in this business. We have that y is a random variable because it has, even though g is a constant, it has epsilon, a random process that is our noise. And y hat is also a random variable because y hat is built from our samples, and therefore it is also a random variable. Now let's start basically breaking down this error, this distance, in its components. So first of all, g itself for this particular x would be some other value, let's say down here. G is a constant in the sense that it's a function, but g of x is a constant at this particular value, and it's a constant in the sense of not being a random variable, right? It is just a plain old normal mathematical function. Now, there is an important relationship between g and y, which is that g is the expectation of y. If you think about taking expectations here, the expectation of y by linearity of expectation is the expectation of g. It's a constant, so it's g itself, plus the expectation of epsilon. What did we just say? Epsilon is zero mean noise, therefore it has zero expectation, right? So the expectation of y is itself g. Now, this piece right here is epsilon, obviously, and what about this piece? Well, it's g minus y hat. And so now we're going to try to, this is the difference between our prediction and the ground truth. Not the observation, but the ground truth. And so we're going to dig a little bit deeper into what it's made of. Because now we're going to think, okay, what happens when we look not at this one particular sample, but at all possible samples that we could have drawn? So when we ask those questions, we're starting to ask questions of expectation, right? Because we happen to have this one observation right here, y hat, for this particular instantiation of the model. But if we had a different sample, right, it would produce a different prediction, right? Our model would have ended up with slightly different parameters. It would make a different prediction. So we can ask, what is the expected value of y hat of x? In general, it's going to be different from y hat. It'll be somewhere, let's put it in here, right? So we can further break down this distance between g and y hat into two more pieces. The distance from g to this, which is g minus the expected value of y hat, and that expected value minus y. Why are we making this breakdown of this distance and into these three parts? Well, because they each have actual meaning. This one is a random variable and this one is a random variable, but these two in the middle are fixed, first of all. These two right here are constants because the expectation is a constant. So we have two constants and two random variables. Now, first of all, let me clarify that the fact that they're ordered like this is a matter of illustration convenience. We could put these anywhere, and obviously some of the signs would be different. The algebra works all the same. So since this is not a mathematical proof, but an illustrative derivation, sort of an illustrative discussion, we've chosen to order them this way just so that the diagrams are clear, but the actual algebra works no matter what. So again, what are these pieces? This is our observational noise. What is this related to? Think for a minute. This is the difference between looking at the model prediction in expectation and the thing it's trying to model. This is bias. Well, actually, minus the bias, because that is the definition of bias. The definition of bias is what is the expected value of my estimator minus the true thing it's trying to capture, right? That is the definition of bias, and that is exactly what this quantity is. It's with a minus sign, right? And that's because of the way we drew the diagram. And what about this piece? Well, this is the kind of thing that goes into the topic of this lecture, the first topic of this lecture, variance, right? What is the variance of y hat? It is the expected value of y hat minus the expected value of y hat, quantity squared, right? So if we were to compute this thing squared and take its expectation, that would be the model variance, right? So this is basically the building block, the heart of the model variance. This is the bias, and this is the observational noise. So what we've done is we've broken down our error into 3 interpretable components, and we're going to use that to then look at the entire modeling risk. So our error has been now decomposed. This is the diagram we had. We've decomposed our error into 3 parts: observational noise, bias, and the building block of the variance. The model risk is what? The model risk is this. The model risk is the expected value of the square of this quantity. Right? That is the definition of model risk. You can go back to earlier parts in the lecture to refresh your memory. That is the very definition of model risk. It's this quantity squared expectation. And as it turns out, so this we're saying square this. So this is made of 3 pieces. Let's say A, B, and C. So what we're saying is A plus B plus C squared and take expectation. Well, it turns out that A plus B plus C squared and expectation ends up interestingly looking like this. The first one squared, expectation. The second one squared. This thing is a constant. This thing is a constant. So expectation is just itself. It's just a constant. And the third one squared, expectation. So, and obviously you would think A plus B plus C squared would be A squared plus B squared plus C squared plus 2AB plus 2AC plus 2BC, right? There's cross terms in the product of the sum of 3 things. Nope, not in this case. In this case, the algebra is such that all of those cross terms go away. All of those cross terms go away, and we end up in a situation where, in expectation, A plus B plus C squared is A squared plus B squared plus C squared. We only end up with the square of each one of these, and none of the cross terms survive the process. Now, again, that is the kind of thing that you do need to prove, and we will provide you with a notebook where you can work out the algebra with a set of notes that do the proof. So this is not that proof, but we felt that it was much more useful and much more illustrative to work out how those pieces are structured so that you know how to interpret them rather than grinding through a lot of math and detail. Because what we have now is that we've broken down the model risk into the expectation of epsilon squared. Well, epsilon was our zero mean process. The expectation of it squared is its variance, right? Because remember, the variance of a quantity that has zero mean is expectation of it squared. And so the expectation of epsilon squared is nothing but sigma squared, the variance of our observation. This was the model bias with a minus sign. Since we're squaring, it doesn't matter. So this is model bias squared. And the third piece is the variance. By definition, is the variance of the model. So we've been able to say that the model risk is additively made up of 3 pieces. And this is so important that we're going to take a whole slide to sort of talk about it in more detail. The model risk is made up, in words, of observational variance, the square of the model bias, and model variance. These are the 3 components of our model risk. Mathematically, this is the equation that we had there. Sigma squared is the observational variance. This term is the model bias squared, and this term is the model variance. Now, it's important to observe that these 3 terms are dimensionally consistent, meaning they have consistent units. You may think that there's something funky going on here because this is a square and these are not squared, but think about it for a second. Variances are quadratic functions, right? Whatever the units of y the observations are, let's say feet, this would have units of feet, and therefore this would have units of feet squared. The units of the model risk would be feet squared. So, and variance has units of the noise, which would have to have the same unit. So variance has units also of feet squared. Model variance would also have units of feet squared. Model bias has units of the model prediction. So we have to square the model in order for this whole thing to have the same units squared everywhere. So There's nothing funny there. It's just that we're combining things that are intrinsically quadratic functions with something which is a linear function, so we have to square it so that everything is dimensionally consistent. Okay, that's just to clarify that point that may throw you off for a second, but the important point here is this nice additive decomposition that goes back to our little diagram back here that basically says, after we take expectations of these things, of this entire set of errors squared, because we always measure our errors squared, right? We still end up basically with the risk of the model being the square of this, the square of this, and the square of that in expectation, and nothing else. So it's a really nice and elegant result. Let's get back to where we were. Before we continue, a little side note: we've used in the past, and obviously in the actual constructions, we express our model y as a function, and it's a function that has some unknown parameter vector theta. Theta itself is not random, but we produce an estimate. The optimal estimate that we obtain after we go through our optimization processes is based on the samples. So our estimate theta hat is a random variable, and so our actual fitted function f sub theta is just another name for y hat. F sub theta hat with our optimal estimate is just another name for our model y hat. We could have done all the algebra carrying around this function, this f sub theta hat notation. It would have just been more Greek letters to keep track of, and so we did it with y hat for simplicity and because it's a little bit clearer, but this expression is completely equivalent, and it's nothing but notation. You can think of f theta hat as a synonym for y hat. Okay, now this actual decomposition, this graphical discussion we've had, as I said, is not a proof. We have provided you with a notebook that has an actual derivation of this bias variance decomposition, a notebook that Professor Ardekari nicely wrote up in the spring. And so you should grab this notebook. It's just a notebook with math, and work that algebra through yourself on a piece of paper. If you can also watch some of the lectures in 2018 where we actually did that derivation in class with an iPad in full, so you can watch one of those videos if you're curious, or come to office hours, because the algebra, that is where you basically have to provide arguments to make all of those cross terms go away, right? We didn't do that. We just said that happened today. But we think that the key insight that you need to draw from this lecture is really an understanding of the structure of this problem. And this is nicely illustrated in this figure, which you may have seen. This is a cartoon. This is not a data plot. This is a cartoon, but it's a cartoon that kind of shows what happens in this process where we have trade-offs. Because what we are doing here, since we basically don't have a whole lot of control over this, if we were trying to reduce our model risk, we're effectively trying to make these two things smaller. But the problem is that they sort of fight each other. If we want to reduce model bias, if we want our model to be less biased, we tend to make it more precise. Well, that tends to happen by adding more things to it. But the problem is, as we add more things to it, the model begins to have more variability, because it basically learns from the noise. So as we give it, if we did give a different sample, it would produce a different output. And so effectively there's a tug of war between reducing model bias and reducing model variance. And this is what this figure tries to sort of illustrate in a slightly cartoonish way. As we make our model more complicated, yes, its bias does go down, but its variance tends to go up, which means these two are in trade-off. So what we're looking for is the place where we've gotten the bias down enough to give us good predictions before the model variance begins to go up, because our error is the sum of these two plus some sort of flat constant, which is the observational noise that is not plotted here. And as we add these two, there is the optimal point where the total error is lowest is basically where these two kind of hypothetical lines cross. This is not exactly how we look for these optimal values, but it is important to keep this picture in mind because it underlies the kinds of analyses that we do to actually find our optimal values. And so to kind of wrap up, our goal in modeling is basically to try to minimize all of these three sources of errors: observational variance, model bias, and model variance. The observational variance is for the most part out of our control. In practice, you may have some control over it, but it's basically at the data acquisition time. You have to think how you do your sampling process, how you design your surveys. If your data comes from physical instruments, how do you calibrate them? Do you buy more expensive equipment? Do you build a new instrument, etc.? Once you've done that, which you should think about, it's kind of fixed, and at that point you get what you get, right? So the next two knobs you have left, as we said, are these other two, where you are balancing the trade-off of reducing model complexity but getting a lot of bias versus increasing model complexity at the cost of getting a lot of model variance. And so this is sort of the game that we play. However, there is one important point to keep in mind, which is that domain knowledge matters. We said that earlier when we discussed modeling, and I want to revisit that as the closing point of this lecture, which is that having the right model structure actually matters. And I want to illustrate this with a real example from the history of astronomy. The Greeks in Ptolemaic times had a model to describe the observed behavior of the planets in the sky. It turns out that if you track the motion that we see of the planets in the sky, they appear to go back and forth. They appear to move forward and backwards at some point in time. This is called the retrograde motion of the planets. And that's because, as we know today, we're all moving around. The Earth is moving and they are moving, and sometimes it seems like we're moving past each other back and forth. But the model that the Greeks constructed, the Ptolemaic model of astronomy, was that the Earth was at the center, and that the planets, because they were heavenly bodies, and there was sort of a religious reason to think that the circles were the perfect shape for the motion of heavenly bodies, so that the planets should move in perfect circles around the Earth. Well, it turns out that if you just make them move in circles, you don't get this kind of behavior. But what they did was they said, well, it's circles upon circles. So instead of just the planets moving in a circle around the Earth, they actually move in little circles on top of other circles. Funny enough, if you actually build a complicated enough set of gears, like those little spirograph toys, that you can draw figures like this, as those toys show. You can draw very complicated figures like that by having offset circles moving on top of other circles. You can make very accurate predictions of the motion of the planets as we observe them from Earth using circles upon circles. There's actually, for those of you who have seen some signal processing, there's a Fourier analysis connection there. But the point is, you can get very high accuracy in this case with an extremely complicated model with lots of features. And then along came Copernicus and Kepler, who said, hey, stop. How about we put the sun in the middle? And if we put the sun in the middle, Copernicus said, we can have the planets moving in circular orbits and everything looks fine. And if the sun is in the middle and the Earth is moving around in a circle, and then the other planets are also moving around in circles, we actually see this kind of behavior. It turns out that wasn't quite right. Kepler came along and said, actually, almost there, but it's actually elliptical orbits, and the sun is in one of the foci of the ellipse, and then the planets move in ellipses around it. This is a far simpler model than the very many circles that the Ptolemaic model needed, and it makes predictions that are just as good. So this is an example where it wasn't about reducing model, where you can get both high accuracy and low bias, but because you capture the right model structure. And so this is sort of a closing thought to keep in the back of your mind, that getting the right model structure matters. So modeling is not just about throwing kind of spaghetti at the wall to see what sticks. It's not about throwing more and more features into your model until you get something that works. Sometimes it's also about thinking, what are the right things to use in the model? Not just more of it, but what are the right ingredients to make a good model? So with that parting thought, we conclude today's lecture. Thank you.